Here's some calculator methods to find partial sums and series sums. The first one is using functions that are already in your calculator. What you're going to do is start off an example. Let's say we wanted to find or estimate this series. And that's the one in the previous video. Okay, so we go into sequence mode over here. I'm missing C. Okay, then go over to sequence and enter that so you're in sequence mode. Then go to second list, and second list is under the stat key, so under stat. And what you want to do there is go down to this sum and hit enter or hit number 5. Then do second list again, which is stat, second list. And this time go to ops. And the first time you went to math. This time you go to ops and select sequence. And when you do that, this menu comes up on a TI-84. 83, you'll just enter these things in one at a time. But anyway, the expression that you want is you put that in, and we want 1/2 to the n minus 1. So we're going to do that, be safe with the parentheses. The variable is the n, which automatically when you hit the x theta n key, puts an n there because you're in sequence mode. Okay, you're going to start at n equals 1. That's always. You're going to end. Now, we're going to do infinity. We want infinity. So our version of infinity is about 100. 100 terms all summed up. That's going to get you pretty darn close to the actual limit for the series. You're going to step by ones, so you add up every individual sequence term from n equals 1 to n equals 2, n equals 3. Now you arrow down to paste and hit enter on that, and it pastes it on your home screen. This stuff here, actually what's pasted there is the expression inside here. This part, you're going to have your 1/2 to the n minus 1. Then you're going to have a comma, n, then a start, then an end, then a step, like that. That's all the stuff that's going to be inside the sequence, like that. And then you just enter, and it says it's 2, and if you recall from the previous video, that actually was equal to 2. So, you know, we used 100 to get close, but it rounded off to the actual limit. Okay, number 2 method. This uses the Riemann program I'm going to give you. You don't use the integral program, not the integral program. And there's a reason at the end of this video which I explain why that is. Okay, so let's say your an terms are 1/2 to the n minus 1. It's the same example. Let's say we wanted just to do partial sum 3. Okay, so that's a1 plus a2 plus a3. Alright, so then you would, just thinking about what that was, that's 1 plus 1/2 plus 1/4, and that added up to 7/4, which is 1.75. So what you do this time, using this method, is you go into your mode and make sure it's back to the function mode. Then you go to y equals, put that in. You know, I entered it with the parentheses. You know, it's 1/2 parentheses up arrow x minus 1. Since you're in the regular function mode, it'll be x minus 1, so that's what you want. Then I pressed graph after I put the window from 0 to 4 in the x and 0 to 3 in the y. I wanted to show what was really going on here. So you're going to find this sum right here by doing this left rectangle sum on the function, this left rectangle, and this left rectangle. So these left areas of the Riemann program, and the Riemann program only does left and right, which is why it's better for this case usage than the integral program, which I'll explain. So you want to go left areas from x equal 1 to 4, not 3. Now notice we have the 3, n equals 3, but we're not going just to 3, because if you went left on 1 to 3, you just get the first left rectangle, and the second it would stop at 3. You want to get the last one, because what's going on here is that, see, this first height is 1, and the delta x is being set to 1. 1 times 1 is 1, so there's your 1 area. That's the first part of the sum. Then this here is 1/2 times 1, and that's 1/2. So that's a 1/2 area, this is a 1 area. That gets the second one. For the 3, the left is 1/4 high times 1 again. So that's 1/4 area. That gets you this one. So you need all 3 of those rectangle bars. So what you do is you go from x equal 1 to n plus 1 with your program here. So to get the answer, we run this program, Riemann, and the lower limit will be 1. The upper limit is n plus 1. Now you want S3, so your n is 3. So you want to put n plus 1 here, 4. Now the divisions is the n size. It's also the difference of 4 minus 1 is 3. If you put the wrong divisions, you're going to get the wrong delta. You want to get it so that the delta x increment jump is 1. 1, 1, 1. Alright? So then you press enter and it says left sum 1.75, right on the money. That's exactly what it should have been. Let's say you wanted to go to infinity using this method. Okay, so you're over here going to infinity. You can run Riemann, go from 1 to our virtual infinity that we usually use around 100, but I want to make sure I'm going to do this right, so I went n plus 1, so I'm going to 100 with n, so it's the upper is 101, the divisions is 100, and then you put that stuff in, and sure enough the left sum comes out 2, and that's what we had previously. Okay, now here's the explanation of why not just use the integral program, because Riemann is an integral program. What's the difference? Well, Riemann does only left and right, which helps us in this manner. Let's say our sequence was -1/2 to n, and the terms were done that way. Then your x would be 1, 2, 3, 4, and the -1/2 to n's would be flip-flopping -1/2, 1/4, -1/8, 1/16. Okay, so when you put a number in between these two, and that would happen if you were doing the midpoint rule or Simpson, it'd be using that midpoint. Well, that midpoint is a number like 1.5 in between here. That's the 3/2 power. So you're saying -1/2 to 3/2, that's a value that's going to be used in the midpoint calculation and in the Simpson calculation which the integral program does. It has to figure those two out. So if you do it, it'll say non-real. It'll get stuck if you run the integral program. That's because negative 1/2 to the 3/2 is a complex number. It's pure complex. So that's the reason why the integral program won't work, because it yields complex numbers here and there in the cracks as it's trying to evaluate for the midpoint in the Simpson. Whereas the Riemann program only does left and right, and those only land on the boundaries, which are these nice integers here. So it all works out. Just for your information, if you want to know what negative 1/2 to the 3/2 really is, it's negative 1/2 to the 1/2 to the third power. The square root of negative 1/2 is the square root of 1/2 I, and I have simplified it to square root of 2 over 2 I. I is the square root of negative 1, defined that way to create the complex number system. Now, so that originally to the third power is this to the third power, which is square root of 2 over 4 I to the third power, and I to the third power is I times I times I, and since you have this power of I equaling square root of negative 1, these two are negative 1 times I is negative I. That's why you get this. So that answer comes out negative square root of 2 over 4I, and the integral program doesn't know what to do with a y value that comes out complex. Messes up the whole routine.